Hi, thanks so much for coming to my talk today. So I'll be presenting some recent joint work with Ilias, Daniel, and Jerry titled Clustering Mixture Models in Almost Linear Time via List-Decodable Mean Estimation. So I'll start by introducing these problems of clustering mixture models and List-Decodable Mean Estimation, as well as their relationships. And then I'll motivate and situate our results in the literature. So this work is going to study the problem of clustering mixture models. And we're going to and a mixture model is a model of a data generation process where data sets are first mixed with different components with mixing weights alpha I, and k is going to be the number of components. And finally, di is going to be the ith different component. So first, a component is drawn according to the mixing weights, and then a data point is drawn from that particular component. Now, in the clustering problem, we're given a number of, at least the clean variant of it, we're given a number of samples from this distribution M, and we'd like to recover approximately which component produced which data point. Now, in order to make this problem tractable, we have to make a number of basic assumptions about the problem, including lower bounded mixing weights, well-separated means, and well-behaved components. And I'll be more precise by what I mean by each of these. So throughout the talk, we're going to use alpha to denote the minimum mixing weight, alpha I. And in the special case where alpha equals 1 over k, namely all of the mixing weights are 1 over k, we're going to call this a uniform mixture model. Next, delta is going to denote the minimum separation between means. Namely, we're going to assume that for each pair of components I and j, the distance between their means is at least delta. And important to note here is that we'd like that delta is only a function of alpha, this minimum mixing weight, as opposed to the ambient dimension. And finally, by well behavior, I'm going to mean either Gaussian or bounded covariance components. So here, when I say Gaussian components, each di is a multivariate normal distribution with covariance bounded by the identity. And in the heavy-tailed or bounded covariance case, I'm going to use these terms interchangeably. We're only going to assume that each covariance is bounded by the identity and make no stronger tail assumptions. So a popular algorithm for solving these problems is the KPCA algorithm. And a number of works, including Vimpalo and Wong in 2002 and Akliopoulos and McSherry in 2005, analyzed the guarantees of KPCA for the Gaussian mixture model problem. In particular, they showed that at separation roughly root k, we can achieve a runtime of roughly NDK for the clustering problem. And this is the Gaussian mixture case. So a couple of notes are important here. In this talk, we're going to focus on fast algorithms, namely those that run in slightly superlinear or linear time in the dataset size. And if you want only polynomial time algorithm, then you can actually achieve much stronger separation guarantees in terms of the parameter delta, including a work of Liu in this STOC. Moreover, the Vimpalo-Wong algorithm actually shows that if you assume that each Gaussian is actually spherical, namely its covariance is exactly the identity, you can achieve smaller separation, namely roughly k to the 1/4. And to give some intuition for why this KPCA algorithm is useful here, the idea is that because of the Gaussian property, most directions outside of the span of the means are very well concentrated. So in particular, projecting onto this top k subspace of largest variance will effectively collapse all of these other directions and allow you to cluster at rates that are independent of the ambient dimension d. Now, if you're looking at this slide, two questions sort of jump out. And in particular, the first is this runtime of NDK is still off from linear in the dataset size by a factor of roughly k. And in high dimensional regimes where k scales super constantly in the dimension, is this overhead of k really necessary? Moreover, this result is stated for Gaussian mixture models. And a natural question is, can we achieve similar guarantees for the case of heavy-tailed mixture models where we only posit covariance bounds? And a primary contribution of this work is that we effectively answer this question, saying that if we have a heavy-tailed mixture model, we can cluster it at separation roughly root k up to a log k factor in time that is almost linear in the dataset size. So to achieve this result, we actually improve an algorithm for a related problem known as list-decodable mean estimation, which I'd like to tell you about. So list-decodable mean estimation can be thought of a majority outlier model of robust mean estimation, where we say an alpha fraction of your dataset is drawn independently from a ground truth distribution D. And here you should think alpha is much less than 1/2. which of course means that 1 minus alpha fraction of the dataset is not drawn from D. And in fact, we posit no assumptions on this remaining fraction, and they can be put adversarially in the support of D. And we'd like to produce a list L of candidate hypotheses when given this dataset, such that at least one element of the list is close to the mean of the true distribution D. We're going to be working in a fairly challenging setting, where all we assume is that the ground truth distribution D has a bounded covariance. And we're going to assume the information theoretically minimum number of samples, roughly D over alpha. And finally, the error is going to be measured by the distance between the closest hypothesis with the ground truth distribution mean. This problem has a number of applications which have been well studied in prior work, including crowdsourcing applications and stochastic block model inference in semi-random models. But a particular relationship that will be well explored in this work is this relationship to the problem of clustering mixture models. So since this problem was introduced by pioneering work of Charikar, Steinhardt, and Valiant, who gave a polynomial time algorithm for this problem, the runtime has been brought down substantially by a number of algorithmic works to roughly ND over alpha. This is attained last year by the same set of authors as for this paper. On the other hand, for the related special problem of clustering Gaussian mixture models at separation roughly root k, or 1 over root alpha, the runtime actually has not been improved in almost 20 years. A work of Akliopoulos and McSherry presented a runtime of roughly ND over alpha for this problem. So as a major contribution of this paper, we present an algorithm for list-decodable mean estimation, which achieves runtime roughly ND up to a subpolynomial factor. We also provide an efficient reduction from the clustering heavy-tailed mixture models problem to the problem of list-decodable mean estimation, which achieves an overhead of roughly ND up to a factor n over alpha. So to achieve our results, our algorithm effectively synthesizes two previous algorithms in the literature and shows how to improve upon both of them. So one is the work of Diakonikolas, Kane, and Kongsgaard, who used a multifilter type approach, which I'll describe in more detail later, to achieve a polynomial runtime. And the other is the work of DKKLT last year, who achieved an ND over alpha runtime. So in particular, this latter runtime used powerful tools from the semi-definite programming regret minimization literature, but unfortunately relied on KPCA to implement their steps. And this already is too much if we're trying to aim for an almost linear runtime. On the other hand, this work of Diakonikolas, Kane, and Kongsgaard showed how to use 1D projections to implement an algorithm. But because of the nature of their algorithm, new tools have to be developed in order to synthesize these approaches, which I'll go into next. Okay, so the next section of the talk will just be our reduction from the clustering problem to the list-decodable mean estimation problem, so that I can focus on the latter problem for the remainder of the talk. So to see the relationship, consider the case of uniform mixture models where alpha is roughly 1 over k. So on the top right, I've posed the list-decodable mean estimation problem that I've introduced earlier for this special case. Now, the observation is that in a uniform mixture model setting with k different components, we can think of each of the different components as the ground truth distribution in the list-decodable mean estimation problem. And because a 1 over k fraction of our data set is generated from this component, it satisfies the hypothesis of list-decodable mean estimation. Now, the upshot of this is that any list decoding procedure necessarily returns means close to each component mean, because any one of these components could very well have been our ground truth distribution. So we make this reduction rigorous in our work. So to set up the problem, assume that we're given a number of samples from a mixture distribution where I'm allowed to mix in a small number of adversarial points. And here this corruption parameter epsilon will be bounded by alpha over 4. I'm also going to assume separation delta of at least roughly 1 over root alpha. So this is information theoretically optimal for heavy tail distributions. And as input for my reduction, I'm going to take as a hint a list of candidate means, which contains at least one candidate mean at distance delta from each ground truth distribution mean. I'm also going to take a number of samples produced by this mixture model. And the goal is to output a 99% accurate clustering of the input dataset points. Okay. So the idea of our reduction is as follows. So let P be the projection onto the span of the points in our candidate list. And I'm also going to let yi be the projection of xi, the dataset point, and nu j be the projection of a candidate guess hat mu j contained in our list. Now, the observation is that by Chebyshev's inequality and the triangle inequality, all of the points produced by a almost all of the points produced by a true component di will lie very close to the true mean, or in particular the list component which is close to the true mean in this projected space. And therefore, if we simply throw away all the candidates who don't have that many nearby points, then we can prune down the set of things we're considering. So more formally, we show that if we simply throw away all the candidates who in the projected space don't have too many nearby points, roughly alpha n over 2, then if your candidate mean was close to a true mean to begin with, you will survive the pruning. And then if you are far from every single candidate mean, then you will certainly get pruned with high probability. And now what this effectively allows us to do is define an equivalence relation on the surviving list elements, such that if you just round each data point to its nearest surviving candidate, then this will form an effective clustering. And to speed up this reduction, we use numerical linear algebra techniques to improve the runtime of a number of these steps, but these details are mostly straightforward, and I'll defer it to the paper. The overhead of this reduction is n times d, near linear in the dataset size, plus roughly n over alpha, which can be thought of as the cost of assigning each point to its closest candidate hypothesis. And I'll mention that the paper also contains a number of improvements under stronger assumptions on these components, but I won't go further into it in this talk. Great. So next, I'd like to introduce a main technical contribution of this paper, which is an alternative filtering technique based on semi-definite programming technology. So to better motivate this problem, I'm going to start by the simpler problem of the majority inlier model of robust mean estimation. So here we're assuming that a dataset is drawn independently from some ground truth distribution D, and then an epsilon fraction, where epsilon is less than a half, is replaced by an adversary. And here the distribution of D is assumed to be bounded covariance. So a popular framework for attacking this problem is the idea of variance-based filtering. In particular, prior work by Diakonikolas, Kamath, Kane, Lemotre, and Stewart showed that anytime you can identify a large variance direction in the data set, it must be primarily caused by these adversarial points. And therefore, a takeaway is that anytime the empirical covariance is too large, we can make progress towards a sanitized data set by using this high variance direction to filter our points. So this is a win-win criteria. Either we're in the case of a bounded covariance and the empirical mean is good, or we're in the case of an unbounded or a large empirical covariance and we can sanitize our data set. Now, in order to turn this into a fast algorithm, it's suggested that we want a way to quickly decrease the operator norm of our covariance matrix. And Dongley and Hopkins showed how to effectively use STP regret minimization technology, known as matrix multiplicative weights, to design a smarter filter, which quickly decreases the operator norm of our empirical covariance matrix. As an upside, this has spawned a number of follow-up works based on the connections between robust statistics and powerful semi-definite programming machinery, including the prior algorithm of this group of authors. However, on the downside, this reliance on this matrix multiplicative weights framework relies on these mirror descent type arguments, which are known to require a number of consecutive iterations in order to make progress. In particular, they don't make monotone progress at every single iteration. So for use in an algorithm such as the multifilter of DKK20, which has a number of different steps, types of steps it has to interleave, it's difficult to reason about how these different steps will affect the progress of the procedure if we don't have some sort of monotone progress criteria. So this motivates a new framework. Now, in our work, we show that there exists such a one-shot potential reduction framework, which I'm going to denote by MMW in quotation marks for the remainder of the talk, to be our one-shot reduction process. So defining MT to be the empirical covariance matrix with respect to a set of weights that we're going to maintain at every iteration, and defining a potential to be the trace of a power of this covariance matrix, we're going to show how to decrease this potential by a constant factor in each iteration, monotonically. So the way we do this is we give a key technical claim, which shows that if we can design a set of weights WT plus 1 such that the induced covariance matrix has small matrix inner products with MT to the 2 log D, namely it's bounded by O of phi t, then we can essentially have the potential up to a polynomial threshold. Now, to understand why this progress criteria is possible, note that if we define scores based on the the quadratic forms of recentered points with MT to the 2 log D, then we expect the average good score to be roughly phi t, or at least bounded by phi t. And therefore, anytime the sum of the scores is much larger than phi t, we can make progress towards sanitizing our data set. Now, by recursing on this claim, in a polylog number of iterations, we can bound the potential by roughly poly d. And this is enough to ensure that the covariance operator norm is bounded as desired. Okay, so finally, I'm going to tell you about how we use this new MMW-like framework within the context of the multifilter to attain our algorithm for clustering Gaussians and solving the Gaussian list-decodable mean estimation problem. I'll mention that much of the technical heavy lifting in our paper is contained in section 4, where we generalize this fast Gaussian mixture model to heavy-tailed mixture models, but I won't have time to go into that for the talk. Okay, so to motivate this problem, I'm going to first explain the basic Gaussian multifilter of prior work. So here the idea is we're going to maintain some sort of tree of subsets with the invariant that at every layer of the tree, at least one node in the tree representing a subset of data points is saturated. So by saturated, I mean it contains at least half of the good points drawn from the original distribution. And we're going to find a way to partition subsets down the tree to preserving this invariant. In particular, the way that previous multifilters worked was typically the following. Take a 1D projection of your data set onto some direction, say of large variance. Now we're going to identify two cases called the cluster and the split case. And we're going to show that we can always apply one of these. And in the cluster case, we're going to make sure that we're going to prune our original set S into a smaller child S prime, such that almost all of the points lie in a short interval. In the split case, we're going to say we're going to find a split such that two children subsets will satisfy the saturation property. So more formally, in the cluster case, we're going to say the multifilter makes progress if it removes some points and retains this saturation property. In the split case, we're going to say we pass these split criteria if we can guarantee that at least one child is saturated, assuming that the parent is saturated, and the subset sizes don't blow up in a formal sense. Okay, so the main technical claim used in prior work to identify this bicriteria argument is that whenever we're not in case 1, we can always find efficiently a threshold tau and a clustering radius r, such that if I define S1 and S2 to be the set of points less than tau plus r and more than tau minus r along this 1D projection, then these two, I can identify tau and r such that the resulting children satisfy the split criteria. So our main observation is that by recursing upon this splitter cluster lemma, we can effectively partition any 1D projection into short intervals. And this partitioning property will allow us to improve an MMW-like potential in our multifilter tree. And I'll describe this framework shortly. So first, I need to tell you about our improvement to this splitter cluster lemma. And effectively, what we show is that if we're given as input a list of sorted 1D projections onto some unit vector, we can, in near constant time, identify either a cluster procedure or a candidate threshold and a split procedure. In the cluster case, what we're going to guarantee is that all of the resulting points will be contained in a near constant length interval. And in the split case, we're going to be able to identify restrictions to subintervals of the form mentioned earlier, such that if the parent is saturated, at least one child is, and the children do not have size blowup, namely some potential based on the sum of the cardinalities to the 1.1th power is bounded. And we're going to be able to identify either case 1 or case 2 in near constant time. Now, by simply recursing upon this subroutine, we provide a subroutine called 1D partition, which takes as input a projection of our data set onto a 1D line and outputs a number of different children such that each child along this 1D projection is contained in a near constant length interval. At least one of them is guaranteed to be saturated if the parent is saturated. And furthermore, the total sum of the subset children sizes does not blow up by too much. Now, how are we going to use this guarantee within the context of our MMW potential reduction framework? The hope is as follows. If I provide to you a subset of our data set points, the hope is that I can provide a number of children such that the children satisfy these bounded size blowup and saturation criteria that I mentioned earlier, but also that every single child along this process decreases this MMW potential and therefore makes progress. So regardless of which branch is true, we're in good shape. Now, to recap from earlier, we decrease the MMW potential along a given branch if letting MT be the parent covariance and MT plus 1 be the child covariance, the covariance is satisfied the following property, namely that MT plus 1 inner product MT to the 2 log D is bounded by a multiple of the previous potential. So how are we going to use this recursive 1D partition procedure to improve the MMW potential? The idea is that we're going to simply pick these directions V to be carefully chosen directions induced by the previous matrix power. So letting M be the covariance of the parent node, we're going to apply this 1D partitioning technique along a number of carefully chosen directions, M to the 2 log D times a random Gaussian vector renormalized. And the idea is that if I apply this in log many directions, then the guarantees of Johnson-Lindenstrauss say that with high probability, I have in fact decreased the MMW potential. And this is true for every single child. And therefore repeating this procedure quickly terminates. And we're going to just output the means of the different leaf nodes as our candidate list. So I want to tie this back to some intuition I mentioned earlier about how we're breaking this KPCA runtime barrier encountered by previous algorithms. So you can think of our algorithm as trading off a 1 PCA on the entire data set at the top to identify a splitter cluster subroutine with the bottom of the algorithm, which by the time it's reached the leaves is essentially performing K copies of 1 PCA, but importantly, each on 1 over K of the data set. So we bound the depth of the multifilter tree using this new MMW potential framework we introduced, and we bound the width of the tree using the multifilter split criteria, namely the bounded set size blowup. These tools introduce a number of challenges in the bounded covariance setting, but more details can be found in our paper. So thanks so much for checking out our talk, and I hope you enjoyed, and feel free to reach out if you have any questions.